Today is going to be our last lecture in chapter 6. Welcome everyone. And in this lecture, we're going to only concentrate on example 6.2, which is maximizing the selectivity for Trambouze reactions. So let's see what are those Trambouze reactions. Reactant A decomposes by 3 simultaneous reactions to form 3 products. 1 that is desired, B, and 2 that are undesired, X and Y. So you can see that you have reactions in parallel. These gas phase reactions, along with the appropriate rate laws, are called the Trambouze reactions. So we have the reactions are given, A goes to X, undesired, A goes to B, desired product, and A goes to Y, and we have the rate laws as well as the rate constants. The specific reaction rates are given at 300 Kelvin, and the activation energies are E1, E2, E3. They are all given as well in kilocalorie per mole. How and under what conditions? When we say under what conditions, basically we mean the reactor types, temperature, and concentrations. Should the reaction be carried out to maximize the selectivity of B for a given value of Ca0, which is 0.4 molar, and a given value of epsilon naught of 2 liter per second. So again, we said the way that we're gonna tackle the problem of optimization for multiple reactions is through first trying to classify them. Are they reactions in series or reactions in parallel? Correct? Because if they are reactions in series, then you have two options. The first one, the type of the reactor, and the second one. So the first thing is the type of the reactor. The second one is the conditions. Correct? Tamam. This is how you tackle the issue of optimization when you have reactions in parallel. However, if you have reactions in series, so you will concentrate on time, whether it's the actual reaction time or the resonance time or tau. Tamam? Okay, so in this case we have reactions in parallel. So let's proceed. Okay, so the question is, how do we increase the selectivity of B? Well, in order to answer this question, we need to look at the instantaneous selectivity, correct? Because this is how we know what to do. This is what we give us insight into what to do. Okay, so then the question should be how to increase the instantaneous selectivity. Well, let's first write the instantaneous selectivity. Here we have SB against X and Y, because B is the desired product, X and Y are the undesired product. So the selectivity equals RB divided by Rx plus Ry. And we have the rate laws, so we can write the equation this way. Now, what can we do? Any idea? Should we write high concentration, low concentration? Well, unfortunately, it's not very obvious, right? So maybe you want to plot, right? Let's plot the instantaneous selectivity against Ca. So when we plot, now it's clear, right? Now it's clear. Okay. Tamam. Very good. So now we can see that there is a maximum value for the instantaneous selectivity, and that is at a concentration of around 0.11 something, right? Something here. Okay. So if we could operate the reactor at this concentration, the selectivity will always be at its maximum, right? Okay, do you want to find the exact number, the exact concentration? Well, you can read it from the figure, or you can use the derivative, right? Remember, Shabab, we have d S over dCA equals 0 at this location, right? At the maximum value of S selectivity, the derivative with respect to CA is 0. So maybe we can take the derivative. Do you know how to take the derivative of this function? Well, it's very simple. So it's the derivative of the numerator, which is K2 times K1 plus K3 times CA square, right, minus the derivative of the denominator, which is 2 times K3 CA multiplied by the numerator, that is K2 CA divided by the numerator square, K1 plus K3 CA square whole square. So this equals to 0, right? And then we can solve for CA. So let's solve for CA. Oops, doesn't show up there. So if you allow me, I would need to erase all of this. Okay, so as you can see here, that after solving for CA, you will get CA equals the square root of K1 over K3. You have, of course, the values of these K's given already, so you can find the concentration that will give you the maximum selectivity in this situation. Okay, so there we go. We know at what concentration to operate. The question now would be, out of the available continuous flow reactors, which reactor should we use? Well, obviously, we should use a reactor that operates at a given concentration, right? Can we use plug flow reactor? No, because the plug flow reactor, the concentration will vary from the entrance concentration, which is 0.4, right, all the way to lower concentration. And we can see that now I'm not really operating at the optimum concentration. So instead, you will use the CSTR, because CSTR operates at the exit concentration only. You have one concentration inside the reactor. Okay, and of course, I can choose my CSTR and operate it at that concentration. So let's use a CSTR. Right. So how can I make the CSTR operate at the optimum CA? Any idea? Well, I design it in such a way that it will operate at this optimum concentration. How? By varying the volume, because if the volume was too large, the concentration will be much smaller than this, maybe around 0. If the volume was too small, the concentration will be close to the entering concentration, which is around 0.4 molar, right? So I design it. How do we design it? Well, what is the optimum CSTR volume? How do we choose the volume? Well, we design it. So let's start with the design equation. You know, for CSTR, you have V equals FA naught minus FA divided by minus RA from the material balance, right? And if you want to deal with concentration, so this is CA naught times epsilon naught minus CA times epsilon over minus RA. So let's look at epsilon. Is it Does epsilon equals epsilon naught? We always ask ourselves this question, correct? Right? Does epsilon equals epsilon naught? Well, the first thing we should know is what phase the reaction is in. It's gas phase. So should we just rush and say, oh, epsilon equals epsilon naught? Of course not. We shouldn't rush in. Okay, so therefore we should ask ourselves, yeah, maybe epsilon is not constant. How do we know? Well, we go to the equation of state. So we know that epsilon equals epsilon naught times 3 correction factors. Right? The first correction factor is related to Ft, total molar flow rate. Second one is related to temperature, T over T naught. The third one is related to pressure. Correct? Okay, so let's look. Well, if it's a CSTR, we can assume negligible pressure drop. And let's say we are operating isothermally. So let's operate our reactor isothermally. Equals to 1 isothermal operation. Let's look at Ft over Ft naught. Does it increase? Does it decrease? Well, apparently all the stoichiometry is 1 to 1, right? So that means Ft would always equal Ft naught, regardless to how much conversion we have. Therefore, this goes to 1 as well, because there's no change in stoichiometry, or no change in total number of moles. Okay, so we have epsilon equals epsilon naught. That was easy. Tamam. And what about minus RA? Well, we can find minus RA, no big deal. Minus RA equals minus RA1. Oops, so we deal with minus, so everything should be minus. Minus RA2 minus RA3. Correct? Which we have them all, or they are all given. So, yep, they are all given, so no big deal. So you can substitute these equations here. So let's do that. V equals epsilon naught, Ca naught, which is given 0.4, Ca, which is the optimum Ca, which I found, and minus Ra, we said, is simply K1 plus K2 Ca plus K3 Ca square. Tamam. So all of these values are given. We just already calculated what this is, and all the K's are given, so we can calculate the volume, and the volume would turn out to be around 1,500 or 1,600 liters. Okay, so very good. So now we know that the reactor should be a CCR operated at a concentration of 0.112 mole per liter. Okay, and of course we took all the data, all the parameters to be at 300 Kelvin, right? So one would ask, actually, if I choose different temperature, all of the calculations that I've done so far would change, right? Because remember, the optimum Ca, which we called it Ca star, was simply the square root of K1 over K3. So you say, well, if I operate at different temperature, I would get a different Ca, and also I would get a different selectivity. So maybe at other temperatures I would have different higher selectivity. Okay, so I do agree with you. So let's go and check out the effect of temperature on selectivity. Right. So the question now is, what is the optimum operating temperature? Again, we go back to the selectivity, correct? Okay, so selectivity is given, and we already have for any temperature, we already have the optimum C. How did we find it? Remember, Shabab, we found it from ds over dCA equals to 0, because this will give me the maximum S, or actually it will give me the CA, tamam, at the maximum S, and we found it to be K1 over square root of K1 over K3. Okay, so let's substitute here and rearrange. Now we have this equation. Tamam. So, and you know that K can be written as a function of temperature using Arrhenius equation. So let's do that. Okay, so we did that. You know, K equals e to the power minus e over RT. So we did that, and we simplified it. We wrote this for K1, K2, and K3, and we got this relationship. طيب. Now, how can we increase the selectivity? Well, we have here few cases. Let's see what happens if I increase the temperature, what happens if I decrease the temperature, and so on. In order to know the effect of temperature on selectivity, I should know what's the power here, what's the exponent here. So let's concentrate on the exponent. So we have few cases here. Either E1 plus E3 over 2 is less than E2. In this case, we have the power negative. Or E1 plus E3 divided by 2 is greater than E2. In this case, the power is positive. Or we have them equal. Come on. So let's go to case 1. What happens if this was the case? E1 plus E3 divided by 2 is less than E2. Well, obviously, you will have a negative exponent. So you have e to the power negative, right? Which means probably you want to write it in the denominator. Okay, so you write it as exponential of a number, let's call it A, divided by RT. So in this case, if you increase the temperature, the whole power will, or the exponent will decrease. If the exponent decreased, the denominator will decrease. If the denominator decreased, the whole number will increase, which gives you a high selectivity. So if it's case 1, then of course we want to run at as high a temperature as possible. Run at as high a temperature as possible with existing equipment, of course. So be careful of that. You know, you don't want to run too high temperature, then it will be risky because the material of construction will not handle it. And watch out for other side reactions, and make sure that if you run at very high temperature, you don't get side reactions. You will not get now B, which is your desired product, dissociating into other product. And watch out for other side reactions that might occur at high temperature. What if we have case number 2? Obviously it will be the opposite, so you need to operate at low temperature. So run at low temperatures, but not too slow that a significant conversion is not achievable. So make sure that you're running at a reasonable low temperature, because if you run at very low temperature, of course you will have very low rate of reaction. Then you will not achieve an appreciable conversion. Okay, you will not achieve an appreciable conversion. Of course, in this case, you will end up with, if you run at low temperature, you will end up with low rate of reaction, low conversion, low required volume. One would say, why should I stick to this low volume? I'll go to a bigger volume. Well, if you go to a bigger volume, then you're not anymore operating at the maximum selectivity. So be careful. Okay, let's take the third case. Third case, of course, of equal. So it goes to 0, and then you'll end up with only this portion. Okay, which means that selectivity is not function of temperature. So run at the temperature of your choice, right? Not temperature of your choice, which gives you an appreciable conversion. Will give you an appreciable conversion. Okay, Shabab. So we just said that the selectivity, actually the maximum selectivity, which is obtained at the optimum Ca, is not function of temperature, right? We just said that. We just figured that the maximum selectivity was not function of temperature. So we said, okay, we can run at the temperature of our choice. Of course, the temperature of our choice would also be something we need to study, because I know that if I choose higher temperature, the selectivity will not change, the maximum selectivity will not change, but the rate of reactions would be larger, right? And therefore, the required volume will be less. Tamam? But anyway, the suggested temperature was 300 Kelvin, and at this suggested temperature, the optimum concentration was found to be from this figure was optimum concentration was found to be 0.112 mole per liter. The exit, of course, we're going to use a CSTR, so that's the concentration at the exit of a CSTR, and this corresponds to a conversion of 72%. 72% conversion. Tamam? Now the question is, what if 90% conversion is desired? So I don't want to stop at 72% conversion. I want to go to 90% conversion. So that means I'll need to use another reactor, right? Because if you simply say, oh, let's use bigger CSTR. Well, the problem if you use bigger CSTR, then you will no longer operating at the optimum concentration. You will no longer be operating at the optimum concentration. The concentration will be lower. The concentration will be lower, and the selectivity will be lower as well. Tamam? So let's be careful there. Okay, so at this suggested temperature, we said the optimum concentration is 0.112, which corresponds to 72% conversion. If you want larger conversion, that means you have to put another reactor. So which reactor type would you recommend for the second reactor? Would you recommend another CSTR? Tamam? Or a plug flow reactor? Well, obviously, you will not recommend a CSTR, because if you use a CSTR, then you'll be operating at the exit low concentration, correct? So you'll be operating somewhere here. That corresponds to 90% conversion. So if you have 0.4, the remaining is 0.04. Okay, so that's something here, somewhere here, and the concentration is low, therefore the selectivity is low as well. However, you prefer to use plug flow reactor, where at the plug flow reactor the concentration starts high with high selectivity, and then gradually and slowly concentration will drop and the selectivity will drop as well. So you will not be operating at a low selectivity. No, the selectivity will start at high value and then gradually decrease. So that's the best bet if I want to operate at 300 Kelvin. So basically, this is the setup. CSTR followed by plug flow reactor, and of course you can calculate the plug flow reactor, especially if you operate it isothermally as well. The calculation will be easy. Okay, with this we reach the end of chapter 6, so I'm gonna pause for your wondrous applause. Thank you very much, and we'll meet soon in chapter 8. Bye for now.